Hey everyone, today we are diving into one of the coolest and most powerful shortcuts in all of mathematics, the hidden symmetry of functions. It's a concept that's not just elegant, it is incredibly useful.
I mean, really think about that for a second. What if I told you that by learning one simple algebraic test right now, you could totally bypass some of the most annoying, tedious problems you will ever face in higher-level math? Well, you can.
And I am not exaggerating here. Seriously. In calculus, you're going to run into problems that can take pages and pages of work to solve. But if you can spot a certain kind of symmetry beforehand, the answer is just zero, boom, done. It feels like a superpower, and today you're going to learn how to use it.
So let's frame this the right way. This isn't just another pre-calculus topic to memorize for a test. Think of this as a strategic tool, a massive time saver that's going to pay off big time down the road. Okay, let's dive in.
This, right here, is the key to everything. The entire process comes down to this one simple action. You take any function, you replace every single x you see with a negative x, and then you simplify. And what happens next? Well, that's where the magic is.
So let's break down what can happen when you run this test. There are really three possibilities, but two of them are the ones we're really looking for: even and odd.
This slide pretty much boils it all down. If you plug in negative x and the result is the exact same function you started with, we call that an even function. It's like the function just eats the negative sign. This gives it perfect mirror symmetry across the y-axis. But if you plug in negative x and you get the exact opposite of what you started with, meaning every single sign has flipped, it's like the function spits out the negative sign. That's an odd function, and it has this cool rotational symmetry around the origin.
Of course, there's always a third option, right? Sometimes the result you get isn't the same, and it isn't the exact opposite. Maybe some signs flip, but others don't. In that case, the function is just neither. And that's totally fine. In fact, most functions out there actually fall into this category.
Okay, theory is great, but let's get our hands dirty and see how this test actually works in the real world. We're going to run through 3 examples, starting simple and then getting a little more tricky, just to see this thing in action.
We'll start with an old friend, a simple parabola. You know, just looking at it, you can probably guess that this has y-axis symmetry. But guessing isn't good enough in math. The algebraic test is how we prove it for sure. So we just follow the process. We replace x with negative x. That gives us f of negative x equals, in parentheses, negative x squared minus 5. And, well, you know when you square a negative number, it just becomes positive. So that negative x squared simplifies right back to x squared. Our final result is x squared minus 5.
And would you look at that? We got the exact same function we started with. Since f of negative x equals f of x, we've just proven, algebraically, that this function is even. Simple as that.
Okay, next up, let's try a cubic function. The process is going to be exactly the same, but pay close attention to how the different exponents change the final answer.
So, once again, we swap in negative x for every x. This gives us g of negative x equals, in parentheses, negative x cubed, minus 4 times, in parentheses, negative x. Now, a negative number cubed stays negative, so negative x cubed becomes negative x cubed. And then, negative 4 times negative x becomes a positive 4x. So our final simplified result is negative x cubed plus 4x.
Okay, now look closely at that result. Negative x cubed plus 4x, and compare it back to the original x cubed minus 4x. Do you see it? Every single sign is flipped. It's the perfect opposite. In fact, if we factor out a negative 1, we see it's just negative x cubed minus 4x, which is exactly negative g of x, and that is the textbook definition of an odd function.
Now for our final example. This one's a little tricky, and it's designed to show you a really common trap. I mean, if you graph this function, it looks perfectly symmetric, but is it even or is it odd? Let's not guess. Let's trust the test.
So we plug in negative x, which gives us h of negative x equals, in parentheses, negative x minus 2 squared. To simplify this, let's try factoring a negative 1 out from inside the parentheses. That changes negative x minus 2 into negative times x plus 2. So now we have negative times x plus 2 squared. When you square that whole expression, the negative sign out front just becomes positive, leaving us with x plus 2 squared.
So let's check. Is x plus 2 squared the same as our original x minus 2 squared? Nope. Is it the exact opposite? Also no. Therefore, the function is neither. And this is a super important lesson.
While the graph is symmetric around the line x equals 2, it does not have the specific y-axis or origin symmetry that we are testing for.
You know, that last example leads us perfectly into a few common pitfalls. These are the small mistakes that are really easy to make, but they're also really easy to avoid once you know what to look for.
First, don't just look at the exponents and think you know the whole story. A function like x plus 1 squared has an even exponent, but that little horizontal shift completely breaks the y-axis symmetry, which makes it neither. Second trap. Don't assume that just because a polynomial has an odd degree, it's an odd function. Take x cubed plus 1. That plus 1 is a constant, and it shifts the graph up, which breaks the origin symmetry, so it's neither. The bottom line is this: you have to run the f of negative x test every time to be certain.
So why does any of this matter outside of a math class? Well, it turns out this whole concept of even and odd functions is actually fundamental to how our entire digital world works.
Yeah, really. From the music you stream, to the Wi-Fi signal connecting you to the internet, to the very sound of my voice right now, it all relies on something called signal processing. And at the heart of signal processing is a powerful idea called Fourier analysis.
And this is the big takeaway. Absolutely any complex signal, music, Wi-Fi, whatever, can be broken down into a combination of simple even waves, which are basically cosines, and simple odd waves, which are sines. Engineers use this every single day. If they know a signal is even, they don't even have to waste time calculating the odd parts, which literally cuts their computing time in half. It is an incredibly efficient system, all built on this simple foundation of symmetry.
So the next time you look at a graph, or maybe even just listen to a song, think about the underlying balance and structure that's hidden there. This powerful mathematical idea isn't just stuck in textbooks, it's encoded into the very fabric of our technology. It really makes you wonder, what other hidden symmetries are shaping the world all around us?